begin, let me just ask you if you have any questions about superconductivity in general, superfluidity, any particular thing from the lectures, the article you read, anything at all, just to get you into the mood for superconductivity now. So let me ask, what is your picture of the order parameter? I'm talking now about, let's say, a superfluid. Let's think about a simpler situation than a superconductor. So it's made up of bosons. What is your picture? How do you visualize the order parameter? Just starting to talk about how people visualize the order parameter of the superfluid or the superconductor. Anybody wants to start? It's up here. Yeah. It's good to talk about it because we want to be sure we have an idea about this object. So I'm writing things and lots of things follow from that, but let's stop at step one and say, do we understand what this means physically? Anybody else wants to give some idea about this object? So let's be very concrete. I have a box, I have a system with all these particles, right? They're running around. What exactly would I call an order parameter in that bunch of bosons that I have? Anybody, you want to start? Start at this end.
Is it like the proportion of particles that act as a single atom?
Yes, that's a start. So what he said, these atoms are acting as individual particles. You can tag each one, red particle, blue particle, pink particle. But then they start to act as one, which basically means that quantum statistics starts to play in. But what does that really mean? Let's make it even more concrete. What could you measure about it to say, aha, I have a superfluid?
That's a trickier question.
Okay.
Just like, what do I envision?
Okay, just go back to what you envision.
I mean,
let's go back to the envisioning part.
So I kind of just picture like an energy ladder and more particles piling into the bottom state.
Yes.
And you can talk about that picture as a function of position, or once it's completely condensed, it's the same everywhere.
Yes. So let's go step by step. So very good. That is, so all of these ideas are flowing in, that the things are losing identity. And exactly the way to visualize is, think of some eigenstates. So we are thinking about non-interacting particles. Okay, so that's what makes things easy. These are non-interacting. There's no Coulomb, no interaction. All this E square over C physics that we saw in the quantum dot, which made things complicated. Every time a new electron came on the dot, we had to recalculate those energy levels. None of that is happening here. These are non-interacting particles. That's useful. They don't have to be, but they can be. This question can be addressed at that level as well, which is nice. So non-interacting states. So if it is a box, these are just momentum states, k equal to 0. If it's a harmonic oscillator, then, if it's a trap, harmonic trap, it's harmonic states. But whatever it is, it's some set of single particle states. And as was just mentioned, as temperature drops down, more and more particles basically condense, that's the word, they condense into the lowest eigenstate. So the order parameter becomes a measure of how many particles you have in the lowest state. Now this is where the identity comes in. So right now I've just said so many particles are in this one state. If I were to try to write down a wave function for these particles, I would have to write down a product state, right? Because a wave function for this would look like, well, psi r1, psi r2, psi r3, because each of these is, each particle has some position, but then you have to symmetrize it because they are bosonic. So you have to put in the statistics and symmetrize it. And at the end of the day, you get a wave function for the entire system. And from that, we are just talking about a wave function for this part of it. So this is now a many-body wave function for just those condensed particles. Okay? And that's what this is. This is now the condensate wave function. So think of the order parameter as a condensate wave function. It's literally like writing down a wave function for a single electron. It's no more complex at some level, except there are n particles participating in this wave function. Okay? But it behaves like a single entity. And that's where you should remember that movie by Klettner. And he said there's an identity crisis, and you also mentioned that. They lose their identity. And that's because they are exchanging, so you cannot now tell this is particle 1, that's particle 2. You can't tag them anymore. So that's the object. Is that sort of clear? What a little better understanding of what the order parameter is? Yeah.
So, I mean, for like the ferromagnet stuff, so my kind of how I thought about the order parameters, I guess something that's 0 below or above the critical temperature and above below TC if you're continuously or discontinuously jump somewhere. So how does
that was too fast. Say that again.
So
the magnet, and you said okay, say that again.
So like order parameters in general, above TC, it's 0.
Yes.
And then below TC, it'll go to something non-zero.
Yes.
Either continuously or discontinuously.
Right.
TC or something.
Right.
So how does that fit in with
Yes.
this wave function?
So how does that fit in with this? It fits in because this has exactly the same property. Okay, the order parameter must have this single property. It must be a measure of order, which means above TC, it must be 0. Below TC, as you said, it could jump if it's a first order transition or continuously grow below TC. How does that show up? It shows up through this. This algebra takes you to that. So let's go through this part slowly. Okay? So all the time visualize in your mind this condensate wave function. And what you're saying is the free energy is basically describing there's some normal state energy, and then there is another part which basically says that if you had magnetization, the free energy would look like this. Similarly, if you had particles which were condensed, this is what the free energy would look like. And then you basically, the difference is that this is complex. So you take a variation. I'm just going to repeat very quickly. You've seen this before. You allow psi star to change by a little bit, and then look at the change of the free energy because of changing psi star, and that gives you this working equation. This is called the Ginzburg-Landau equation number 1. There's a number 2 as well, which deals with currents. But we'll come to that. So this is Ginzburg-Landau equation number 1, and when you solve it, it basically gives you 2 solutions. So this is the answer to your question. It gives you 2 solutions which says that above TC, the free energy looks parabolic with a minimum at psi equal to 0. So obviously, for all temperatures above TC, the minimum will happen at psi 0 equal to 0. So your order parameter is 0 for all temperatures above TC. For temperature less than TC, this alpha parameter has to change sign in order to give you a minimum which moves away from 0 to another point. Okay? And when it moves away to another point, and I've tried to draw this Mexican hat potential by saying it's in the complex plane at some other point, so the 0 point becomes a maximum. The minimum has moved to another point, which means your order parameter has now become finite, below Tc, just like the magnetization story. And its behavior in temperature is this, from here. So let's plot it. Psi 0 magnitude as a function of temperature. And what we see from here is above Tc it is 0. Below Tc it goes like minus alpha over beta. What was the constraint on this? Beta was pretty much T independent. Okay? Or what we are saying is it's weakly temperature dependent. It doesn't have any particular sign change or singular behavior at Tc. It's some power law, so you can just set it. Remember, this is an expansion only near Tc. It doesn't work everywhere, only near Tc. So it's temperature independent or weakly temperature dependent near Tc. And alpha changes sign. So this is the quantity which is of the form T minus Tc. So it changes sign. So clearly now if I plug it in here, your question?
So solving that equation 1 gives you minus alpha over beta.
Yes.
Just in general. Do we just call it 0 above Tc, sort of phenomenologically? Or is that...
No, you can, what you do is you can just plot f as a function of psi above, for t greater than Tc, now alpha is positive.
Mm-hmm.
So you will get something of this kind, right? So the logic is first you can just plot this as a function of psi. And when alpha is positive, it will give you a minimum at psi equal to 0. So if I take a derivative and I will just find the solution that psi is 0 above Tc. On the other hand, if alpha becomes negative, then at some point I will get this solution. So you're building in the phase transition. So the logic of this theory is the following. It's not a microscopic theory. So one has to understand what is the logic of the theory. You're saying that we know this is a system that has a phase transition. How could we write okay, if it's a phase transition, there must be an order parameter. How could we write a theory that is bare bones theory that has the right symmetry, just builds it on the symmetries of the order parameter? So that's the logic. So you have built in this fact. But then many things start to follow, which is what we are discussing. Okay, so now below Tc, alpha becomes negative, right? So this is not some complex. I don't have to take a square root of a negative number. This is a positive number below Tc because alpha is negative. T has gone below Tc. So this is a minus alpha is positive. So this quantity now then looks something like this. It has a form here, so psi 0 close to Tc goes like T minus Tc over Tc, if I want to write it in a dimensionless way, to the power half. So that's how it is going to 0. It's going to 0 with a half power. And it grows below that and ultimately reaches a value at 0 temperature, which is given by these constants, alpha over beta. So this value here is sort of, so T would go to 0, it's A times Tc over beta, this value here. Okay? It's just A times Tc over beta, square root of that. But anyway, you don't care about that. You don't trust the theory down to 0. Really, you're trusting the theory only there. And it has that form. So does that answer your question? Okay, so this is a continuous phase transition from a superfluid to a normal state. And what is happening in this phase transition? What is happening is below Tc, coming back to this energy level diagram, you had a macroscopic number of particles. So at 0 temperature, this number, psi 0 square, is basically the density and it should have been all the bosonic particles in that 0th level, right? All the particles have come into this level at 0 temperature. So the condensate density is equal to the total density at 0 temperature. What do I mean by condensate density? Psi 0 squared is the condensate density. So another way to think about it, so let me write that. You can define a condensate, just like psi squared. If I gave you a wave function psi for an electron, and I asked you what's the electronic density, you would take psi squared, mod psi squared. So in the same spirit, the condensate density is mod psi 0 squared. And this quantity is temperature dependent, right? And so below Tc, it is starting out with all the particles in that lowest level, lowest energy level of that tower of levels. And as you raise the temperature, some of them are getting excited, but it is still a macroscopic number. But finally at Tc, it becomes of order 1. Everything has gotten de-excited. Question? Yishin? No. We look like we might have a question. Anybody else has a question? Yeah.
So are we setting this density such that if the size of our sample were to double, that the condensate density would double as well, or how is it expressed?
Oh, you can normalize it by the total number of particles. Is that what your question is?
Yeah.
Yeah.
Is it generally, or is it here? I can't really see.
So here it is a density, because it depends. If I define this to be, it's like saying, what is, if I had an electronic wave function, psi of x, and I asked you what's the density, you would take mod psi x squared, integrated over all x, right? And you would get a volume factor from there. So that would give you a number. And you can divide out the number or the volume and define a density. So the operative thing is that you are getting, let's say if I have, the important thing is to think about the momentum distribution. If you remember when we plotted the momentum distribution like this. So K is again those tower of states, that's labeling the tower of states. And essentially at high temperatures, the number of particles in any kth level is of order 1, right? Or much less than 1. So n of k for anything is exponentially, n of k basically goes like e to the minus the energy of beta times that. So this is in the classical limit. So the number of, on average, this is on average, n of k is the number of particles. In any one configuration, there will always be one particle. It's an integer number you will count. But when you average it over many, many configurations, the average number per k state is much, much less than 1 in the classical limit. So it's something like this, right? So this is my exponentially small tail. But then what happens in the Bose case is you start to get, here is 1. You start to get enhanced occupancy of the low momentum states, and then finally you get a macroscopic number. So this is now a number. Let's call it N0, like capital N0. So if I look at sum over n of k, I don't normalize anything. This I can write sum over all k as N0 plus sum over n of k prime. All the k's not equal to, so this is k not equal to 0. Right? I can write sum over n of k as n0 plus this. This of course has to be equal to n total. So, right? So now, if I divide by n total, something which is exponentially small and I divide it by n total, it's going to be a number which is exponentially small if each of these states is extremely lightly populated. Whereas if n0 is a number, so let's say, if suppose n total, let's take some of these experiments in these harmonic oscillator traps. N total is like 1,000,000 particles. It's better to think of million than 10 to the 23. So I have 1,000,000 particles, so this is 1,000,000. And let's say n0 is about 10 to the 5. So then the condensate density would be 10 to the 5 over 10 to the 6, which is 0.1. It's a it becomes, either you can say there is macroscopic occupancy, and in that case I'm talking about n0, or when I talk about condensate density, I have divided it by n total, and then I'm saying it's a number which is bounded by 1, because the maximum n0 can be is n. And in that case, the condensate density would be 1. If it's 10 to the 5 out of 10 to the 6, it's still a condensate density of 0.1. That's something like this. Okay? But if I look at higher temperatures, it's exponentially small, and so basically it goes to 0. Okay, so that was one key point about this order parameter. And then what we showed was that it has, you can plug in this value of psi naught in the free energy formula, this psi square and psi fourth formula. And you can show, basically, when you plug this into that formula, that the free energy below Tc is minus alpha square over 2 beta. Alpha is negative, but alpha square is positive. So this is necessarily negative. And that tells you that the superconductor is more stable, below Tc. And the specific heat then have this linear behavior near Tc. So these are some of the properties we covered. Next thing we wanted to get to is whenever there is a phase transition, there is always associated with it, if there is a continuous phase transition, a length scale which diverges. And so I wanted to go over that length scale diverging. So what that means is a phase transition is associated with fluctuations. So let's draw that picture here again. So this is now psi 0. I'm looking at the mod of that as a function of temperature, and it is going to 0 like this. So here it's like T minus Tc over Tc, as we said, to the power a half. And here, so the point is, so this is a continuous phase transition from superfluid or superconductor to normal. So here's the superconductor, here's the normal. And associated with that, there is a length scale which diverges. So this is now C of T. And this diverges, and it also goes like some C0 T minus Tc over Tc to the power minus. So let me actually just use mu's and beta. So this is beta, that is called mu. And the reason is that some of the exponents we are deriving in class are just mean field exponents, and there are fluctuation effects beyond that which we are not capturing. This blue is not a good idea, I won't write in blue. I like colored chalk, it reminds me of all the sidewalk chalk I played with. All of that hopscotch and so on. It's kind of fun. Anyway, so we wanted to derive this length scale, and the way to do that was to put something which causes, so until now our order parameter was a constant, right? It's like saying I have a homogeneous system, what is the wave function doing? So the wave function is, of course, usually in an electronic system, the wave function is in some plane wave state, e to the ikx. So it is oscillating. In the case of this condensate, so it's useful to remind ourselves that in an electronic case, I would have some phi of x, which could be a plane wave state, something like e to the ikx. And the analog of that for the condensate, remember, is this k is equal to 0. Okay, so the electron could have been in any plane wave state. The condensate chooses to be in the lowest mode. And so it is in a k equal to 0 state. So our psi 0 of x is just equal to a constant. And that constant, we said, was what we call, it's that mod psi 0 that we have found. There's no x dependence here, right? It's just a constant. So of course here we were looking at the mod, which is of course constant for both of them. But there's a special thing about the condensate. It lives in the 0 momentum state. Now what we are going to say is, for this very object, what is its behavior? What is the behavior of the order parameter as I put a wall? And so in that case, the magnitude of the order parameter is now no longer constant. So it's like saying the magnetization. Suppose I had a magnetic system, but now I've put a wall there. So the magnet is not going to have a finite magnetization and then drop suddenly to 0. That makes it pay a huge amount of energy because you are keeping it constant and then you're putting a kink in it at just one point at the wall. The system prefers to adjust to that boundary condition on some natural scale. And that natural scale is what we are trying to find. Okay, so that scale is what's called this coherence length. And the coherence length I derived for you last time. I wrote down one differential equation. I was actually able to solve it exactly later on, which I'm not going to take you through. But I came up with a nice trick, and it may well be there in some of the books. It's not there in the book I'm following, which is mainly Tinkham. But anyway, it's a nice trick, and basically, maybe I should write down the equation we solved, and then. So the equation we solved was the following. It was essentially the Ginzburg lambda 1 equation with a gradient term. Because we said now we have a wall, so that should produce some gradients. It's alpha psi plus beta mod psi square psi. This is what we had before. But then there is another term, which is h bar square over 2m star del square psi. And this is equal to 0. So you can see what is starting to happen is you're getting a Schrodinger-like equation for the condensate part alone, which says that not only does it feel this sort of nonlinear potential generated by the condensate, but there is also a cost, a gradient cost, just like you would have for an electronic system. And these things are just some kind of phenomenological parameters right now. Okay, and from here, then we got some differential equation and we solved that. I solved it perturbatively, but it turns out you can actually solve it exactly. And this is the solution you get, where C is h bar square over 2n star mod alpha. So, so this should be C square. Okay, so you can see most of physics equations are just dimensional, just from dimensional analysis. You can predict all the equations. So you know that energy is h bar square over 2ma square, right? Hydrogen atom. And now, so that's how you get this. Alpha has an energy, because free energy is an energy. Psi was dimensionless. So alpha has units of energy. So that's how you can get this. But this also tells you what is the temperature dependence. Because remember, alpha went like 1 over T minus, so alpha went like T minus Tc. So this clearly then says that the coherence length as a function of temperature must be something like h bar squared over 2m star A Tc, and then I have Tc over T minus Tc mod to the power half. Okay, and this whole stuff to the power half. So what did I do? I just put alpha equal to alpha of t is just A times T minus Tc. So that's what I did. So it has the form C naught. This is some temperature independent piece and a temperature, yeah, that's right, I wrote it inversely. So that's correct. So this is C naught. This term here is basically defined to be C naught. Here's the temperature piece. And I wrote it as minus nu, so that tells you that as temperature goes to 0, this scale is diverging. And so essentially the way to think about C is a scale over which the superconductor is fluctuating. So let's write that here. So C of t is a measure, is the length scale superconductor or superfluid is fluctuating. So let's see if this makes sense. Fluctuating. By that I mean that, again think of the magnet. When I have everything up, you may have thought, you may not like this result. You may want to say, well, I want the length scale to be really long in the superconductor and kind of short away from that. But this length is a measure of fluctuations. So when you are deep in the superfluid or deep in the magnet, that is a very confident object, right? It's not fluctuating. You know your place, and so there is hardly any fluctuation. So the length scale over which the magnets, moments will be tumbling is, a little fluctuation here and there. But as you come to a Tc, now the system is getting confused. Should I be a superconductor? Should I be normal? It's kind of dithering. And so there's a length scale over which this dithering starts to happen, and that grows as it comes toward the transition. So that's how it has the highest transition, highest length scale at Tc. Then again, once it goes above Tc, it's again in this normal state, it knows its place. So it's at the transition, when it is going through this indecision, that the length scale is large, and that's what comes up. Okay. So that's one of the length scales that describes a superconductor. And the other length scale, which is, so actually before that, let me just make sure. Yeah. So that's really all I want to say about C. Any questions? Okay. So the way we will find C playing a role is, here I showed you that near a wall, the order parameter will start to get destroyed. This length scale here, this is the length scale C, and the point is this scale is temperature dependent. So that's how it shows up in So it can show up in an inhomogeneous situation in this way. It can also show up in a completely homogeneous superconductor, just by having length scales over which the superconductor is getting destroyed. Okay, now let's turn to another situation. So what is the so the superconductor, when we discussed some time back, it has two fundamental properties. One is zero resistance, and the other, some people mentioned, was Meissner effect. Now, what is Meissner effect? Let's talk about that. So we haven't really derived zero resistance. That's actually a very difficult calculation because it's a transport calculation. But a way to think about it, I'll give you a qualitative way because we won't really be able to get to transport. A way to think about it is the property of this condensate. It's like the power of unity, literally. So, you know, you have to visualize it in the following way, that you have a system with some kind of disorder, right? And if I look at one electron, this is one electron, it can get scattered here, 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 there, and that produces resistance. Now you have to look at a condensate. And the way the condensate behaves in the presence of disorder is very interesting. You know, we talked about K equal to 0 getting macroscopically occupied. So the way to think about how this would go through in a disordered system, you know, now people will give you all kinds of pictures. Okay, because it is a condensate with so many particles, it doesn't feel the disorder. But I'll give you a mathematical way of thinking about it, which is, you know, very rigorous, can be made very rigorous. And that is the following. This tower of states that we wrote down, right? We said this is K equal to 0, something, something. In K, the eigen label was momentum. Now, you don't have momentum if there is disorder. But so what? You have some label which is the solution of your H0, your Hamiltonian, which is minus h bar square over 2m delta square plus some B of r. This is some scattering impurity potential. Okay, it's a one-body potential which you can diagonalize. And it will give you a bunch of levels here. Let's label them with something. Say alpha equal to 0, alpha equal to alpha 1, alpha 2. So this is alpha 0, alpha 3, and so on. Okay? So, provided this state, alpha 0, is, you know, there are some caveats. It should not become totally localized and so on. I'm not going to get into that. But in principle, I've solved for a new set of single particle states, which includes the disorder potential. And so now, my condensate can just sit in this single particle state. So how did we imagine the K equal to 0 state? It's a constant, right? If I take e to the I 0, that's 1. So the K equal to 0 state was a constant. This state, because there is disorder, is not going to be a constant. Clearly, if I have some hills and valleys, you know, let's say I have some potential which looks like this, etc. Okay, so this is my B of r. Now, clearly, my condensate will try to adjust to it. My single particle state is not going to be constant. It's going to avoid the high hills. So the psi of r will basically look like this. It will avoid the high hills. It will try to stay near the deep valleys, etc., etc. But all the particles that you have, all the bosons that you have, will now condense in this single particle state and macroscopically occupy it. So that's how you can have a condensate fraction which is still huge even when you have disorder. Because all the particles feel the same disorder potential. They are not randomly getting scattered with arbitrary phases And that's what would destroy phase coherence. You know, you have some single particle state, which is non-uniform, but all the particles are in that same non-uniform state. So that's how the condensate is completely robust to disorder. And that's why it does not, that's why the resistance continues to be zero, because it does not destroy that condensate. Okay. So now, so that's the story about zero resistance. Okay, next we come to another very amazing property of a superconductor, and that is the following. So let's at least get the experiment clear.
Can I ask a question about this
Yes.
last picture?
Yes.
We talked about metals last quarter and how you get conduction in the first place. You kind of have to bias it and you shift the Fermi sphere so that you get more positive K states than negative K states, and so you have this drift velocity. So you say that the electrons can condense into a single particle state, but how does that translate into actual conduction through this?
Yeah. So the way it translates is you will see that in just a bit. Usually to get resistance, so let me give you a short answer here and then I will give you a longer one right here. To get resistance, J, the current, must be proportional to E. So this is equal to sigma times E, right? Then we call the coefficient to be resistance or conductance, whatever. So, but J must be proportional to E to get resistance. And what I will show you is in a superconductor, J is not, you don't get this relation. It gets replaced by another term. And that term is equivalent to saying that your velocity, you see, if you didn't have disorder and you applied a field, right, you would accelerate that particle. So if there was nothing that was scattering, an electric field would be proportional, because this is a force, so it would be proportional to acceleration. But by getting all the scattering, we got velocity to be proportional to the electric field, right? Because J is NeV. So the scattering gave rise to a drift velocity which was proportional to an electric field. So what you find in the superconductor is another term. You know, there's the normal stuff which is getting scattered, and the normal stuff has a piece which goes like this. But the the condensate part actually is accelerating under the electric field effect. So that's how you don't get a resistance. So you get two pieces. One piece has a drift velocity, which is when you apply an electric field, the normal part is drifting with some constant velocity. But the condensate part is actually accelerating in the electric field. So that's how you. Okay, so let's go with the Meissner effect, or another way to say this is a superconductor has zero resistance and also it's a perfect diamagnet. Okay, so let's say I take a superconductor. So here's my superconductor. Actually, let me draw it. Here's my superconductor. And if I put it in a magnetic field, so the step one is turn on a magnetic field. let's say I turn it on, I have a north magnet, north pole here, a south pole here, and so obviously I have some lines. So what you will see is above TC, so you have two situations. If the system was not a superconductor, and we show it on the same figure, suppose this was normal, then the lines would just go through this. The magnetic field would penetrate. You know, let's assume that normal stuff doesn't react at all, or it barely reacts. So then you have these lines going through that, and on the other hand, this is the Meissner effect. When you have a superconductor, these magnetic fields are avoided by the superconductor. So the magnetic fields bend around the superconductor, they never penetrate the superconductor. Now how is that possible? What could be happening inside the superconductor to make this happen? So, you know, in other words, this is H. This is also H here. But if I look inside the superconductor, there is no magnetic field. So how is that possible? Why is the magnetic field? So the question that arises is, why does H not penetrate the superconductor? What do you guys know about this? Or maybe you've seen some experiments that show this, or what have you seen about this? Let's start with that very simple demo, which I really love. I should have gotten it today. It's, let me describe it. And I think you must have seen it in one of your E&M classes. And it's the following demo. I have a long tube. This is a metal tube. It's hollow. And you can put a pellet into this. And see what is the time it takes to go through it. Have you seen this experiment? No? Okay, then we absolutely have to do it. Bring it next time. I will bring it. Have you seen this? Okay, so describe to me what you see.
So I think you just drop it through there and you can time it. And then you can put a, I think you put a current through there. I think, or somehow you get a magnetic field through the metal tube and then drop the pellet a second time and it drops slower. Because the field lines are keeping it from moving fast. I can't remember exactly how it works.
Okay, it's the first part sounded right, but okay, it's a very simple experiment.
Are you dropping it back?
Yeah, you're dropping two pellets. So one pellet, so the thing is, if it's pellet 1, which is non-magnetic, and now you can time it, okay, so much distance, gravity, T equal to so much. You look at it, okay, it does work out, a few seconds. And then you do pellet 2.
2 seconds. How long is this tube?
What?
How long is this tube?
It's about this long.
Okay.
8 seconds or something. I timed it in one of my classes. And pellet 2 is, or something.
A 2-foot tube, it takes 8 seconds for a non-magnetic.
She's on Mercury.
Okay.
Huh? What?
I mean, there's nothing interesting about the non-magnetic one, right?
No.
Okay.
Just also.
It's some T naught. You know, in our units, it's a time which we set to 1.
Sure.
And now the question is the next one. What does it mean? Pellet 2. Turns out, okay, you don't put any current or anything. There's no external, it's a very simple experiment, just this tube. It's what I would call not a very, it's a century-old kind of experiment. not like our modern ones that need a lot of gadgetry. So pellet 2 is a magnet. It's a magnetic pellet. And the time, you're waiting, you can go have a sandwich, you can go get some more pop, and it's still waiting and waiting. And it takes a long time to get through. And I'm going to bring it next time you can see it if you haven't seen it. And so that's the effect. And the question is, why is this happening? What is it about the magnet that makes it so slow?
So it's since the magnet is following a changing the flux through you're inducing a current in the field in the opposite direction. So it's
Lenz's law, you know, that good old Lenz's law. Right, you want to add something to that?
No, basically that. The magnet going through the tube causes currents to go through the tube, and that of course dissipates energy. Energy has to come from somewhere, so somehow or other that winds up slowing down the
You don't even need to invoke energy, it's just that it's going down. So the magnetic, if you break up any of this into a little, section, and the magnet is going through that, so the flux through that little disk is changing, and as a result it must generate a current in the opposite direction. So as the magnetic pellet is coming toward the ring, the flux is increasing, and so there must be a current in the opposite direction to oppose that. So what we are realizing is that there are currents getting generated just because this magnet is trying to go through. And it opposes that, and that generates a moment in the opposite direction, which counters the moment of this magnet. And you know, this is Lenz's law. But now, suppose I were to say, well, this, and okay, this is the other interesting thing. It's hard to do, but if you take this metal, and let's say I told you I make it colder. Okay, so I do the same experiment, I make the metal colder. It's still a normal copper metal, but I make it colder. Now what happens? Eric, you want to venture a guess?
So, as you make it colder, the conductivity should increase, right?
Mm-hmm.
So then it should probably resist it more and more. Let's see.
It would resist.
Yeah, because you get more.
Because
current.
you are getting more currents, and so the magnetic moment generated by these currents is going to be larger. And now I can ask the next question: if this metal were to become superconducting, what would happen? So suppose I go all the way, I still have a magnetic pellet coming down, but this tube, the metal tube, is replaced by a superconducting tube. Then what would happen?
Would the pellet not fall through?
Yes. Yes, and that's that levitation experiment many of you have seen. You have, it's in a different geometry, but you have this, you know, you've seen it many times, and I'm going to have you analyze that at some point. It's not as trivial, that levitation experiment. And so we are going to actually, instead of just saying, geez, wow, this and that, we'll actually analyze it and figure out what is the upward force in one of the later. So anyway, if it becomes superconducting, the currents are so large that the superconductor will, the metal pellet will not enter the superconductor. It will feel the upward force like this. So remember, the force is basically given by, it's the gradient of the field, m dot gradient of the field. And so obviously your field here was not bending. Here the field is bending, and that's what generates the upward force. So we will go through that analysis a little more in detail. Yeah, question?
So what would happen if you pushed on the pellet?
You tell me? Suppose you pushed on the pellet and let it be.
Well, it would stop, presumably.
Mm. Might do more than that. What do you think? Say so it's a superconducting tube, you bring a pellet, it's not going in, you push it. Now what would happen?
So I know you can destroy superconductivity by applying a really large field. I don't know if a pellet could pull that off.
Right. So a pellet probably, yeah, you're right. If I really pushed a lot of magnetic field into the superconductor, it could destroy it. But let's say it's a tiny pellet and it's a big tube, and you're trying to, and you push it in a bit. And then what do you think might happen? Maybe somebody should do an experiment on this. But take a stab. What do you think?
It'll either shoot out or just hover.
Yeah, I
Yeah.
think it goes all the way through.
It would probably
Oscillatory?
execute an oscillatory motion, like a simple harmonic motion, because there's a force, but then you overshoot it, and then it's literally set up for a simple harmonic motion in this. But somebody should do that experiment. Could be interesting.
Why? What would it oscillate around?
Around the point where, let's say right here. So there's an equilibrium. So when this magnetic field, this pellet is trying to go in, the magnetic field is bending, right? Because it cannot penetrate the superconductor. That gradient in the field generates a force. And so there's some equilibrium position where the magnet will like to sit. And if you overshoot that, then it generates a back response. And so then you overshoot in the other direction, and then you go back and forth. And so you can analyze that literally as a simple harmonic motion. Because the position it occupies is the equilibrium position with all of these fields bending.
So with a normal metal tube, you just got the conductivity high enough. Could you drop a pellet into the tube from a high enough spot and then see it shoot back out?
So in a normal metal, unless the conductivity went to infinity, there's some scale over which it will die. There's some length scale over which these currents are nothing but eddy currents. And so they decay typically on some scale which is given by the conductivity. So if you made it better and better, it would depend on, so it would depend on the conductivity of that metallic tube. But in a superconductor, since it's infinite, it has the maximum response, and so the magnetic field or the magnetic moment is maximum in this case. But I guess, is your question about whether it could shoot back out?
I'm just
I mean,
little-
at some level, a perfect metal is identical to a superconductor, just in terms of the conductivity. The difference is just that a metal is not so robust. So at some limiting case, maybe it will happen. But a superconductor does it so a metal would do it if the temperature was 0, if there was no disorder, under very special conditions. But a superconductor will show you this behavior at any temperature below Tc and with sufficient amounts of disorder. It will still show this behavior, yeah.
I don't think it's ever going to shoot it out because it's always opposing its motion.
Yeah,
So it's just going to, it
at
will either
most it
oscillate
will-
or at most,
But where would it oscillate?
It'll oscillate if this is the equilibrium and you pushed it with some force.
Why is there an equilibrium whenever there wasn't in the original case?
There is, because you see, like something like this, when you have, so let's see, if I have a superconductor here, and you have a pellet, okay, this is a magnet, this is a superconductor, and there is a field, right? So there is this magnet sits on top of the superconductor at a particular height. That is calculable. Given the moment of the magnet pellet, the height at which it will, when you see these levitation experiments, there is basically gravity which is pushing it down, and the gradient from this magnetic field lines bending which is pushing it up. So you have to balance gravity, mgh, against the gradient. And so depending on the magnetic moment strength, and the weight, there is an equilibrium height that you can calculate where this thing will sit. Okay, now if you push it down a bit, that means you have upset that balance and it will now oscillate about this H naught. That's what I've said. And same thing will happen there. I mean, that's harder to do, but you've seen this sort of an effect. I mean, nobody has these long tubes which are superconducting because they have to be in some dilution fridge. But the same analogous thing you've seen in this thing. Yeah, Eric?
So I was just thinking that what if the pellet is an electromagnet and we put it halfway down the tube and then turn it on? Does it still feel, do we still get these eddy currents that resist its motion, or will it fall straight through the tube? Or will it start to move and then we again get these eddy currents?
So you make it an electromagnet, so you let it go in, then you start it off.
Right.
Start it off, okay. And is it a superconducting wire? Tube?
Yeah, the tube's superconductor. Yeah.
So, yeah. And
That require a lot of energy then to get a current.
so, okay, what do
No,
you
I've
think
just
will
got
happen?
these going into the tube, right?
Yeah.
So Eric's point is that it was
You're
normal.
in,
It was normal to begin with. It started going in, and now you turned on the electromagnet by turning on a current. So you made it magnetize. Now what would happen, right? Will it?
Yeah.
Your point is, will it come out or will it go down? Okay, yeah, food for thought. Think about it. So clearly it would start slowing down, right? Because
Okay.
now, at least at that point, it will start to set up currents.
Okay.
And if I had to make a guess, my guess would be that, okay, there may be a little delay time in terms of how quickly the currents start off. Barring that, the moment the currents start, it will sit at that position. At the position at which you started, a little bit it will drop because there's a transient effect in how quickly the superconductor starts to generate the supercurrents. But my guess would be this, but you should think about it and bring your thoughts also. Okay, so the point that we are driving at here is the magnetic field that we are applying, B, I'm sorry, H. So the net field that we are seeing in the superconductor, B, is H plus 4 pi m. So this is the external field. And for B to be, if there is no magnetic field inside the superconductor, then something must be happening. The material must be generating a magnetic moment which exactly cancels that. So in a superconductor, B is equal to 0, which implies that M is equal to minus 1 over 4 pi times H. Okay? So that's the point about, so this is what we mean by a diamagnet. That the magnetization is opposite to the applied field. And the next question is, what is generating this magnetization? Magnetization is generated due to the orbital effects. Just like in, you can have spin or orbital currents generating magnetization. So here, it's the orbital motion of the condensate density that generates this magnetization. So, origin of M. So again, think of it, it's very profound. I can just say condensate and so on, but it's these million atoms which were sitting in the k equal to 0 state, now are no longer in a k equal to 0 state. They are in a current carrying state. And they together in unison carry current. So basically, if I want to cancel that magnetic field, I must have the currents rotating in a way to cancel that. So let's try to get that. It's coming from the orbital currents. generated by the condensate together. And this is often called the supercurrent. It's often called, that's why I kept saying super, super all the time. This is what I had in the back of my mind. It's called the supercurrent. Just to distinguish it from single particle current, yeah.
Is it wrong that I associate orbital currents with like, bound electrons, whereas in the case of
No, it's the way to think about orbital currents is, when you write the Hamiltonian of some charged particle in a magnetic field, the orbital current will be what goes with P minus EA. It comes with that vector potential, and the Zeeman will be what couples to the magnetic field with M dot H. So it could be due to enclosed shells, but it could be also, like when we talked about, we didn't really, but de Haas-van Alphen effect and all of that, in a magnetic field, when you have just electrons carrying in extended states, that's the orbital current. Or quantum Hall effect, when we talked about what do electrons do in a magnetic field, those are all orbital effects. So that's the thing. And now let's see if we can get some meat on this. So so one more picture here. So basically what I want is to cancel this magnetic field, and what I want to do is to set up some kind of orbital currents like this. So there's a net moment going this way, which cancels the magnetic field that way, and this orbital current is then the cause of why the net magnetic field in the superconductor is 0. So this is the orbital current. So by orbital, what I mean is the super electrons, or the electrons in the condensate, are actually rotating because of the magnetic field. Okay, they are actually going round and round, creating this current.
So are the field lines that you drew actually B?
So these field lines that I drew are B. Yeah.
Right.
So what I want to say is H is this external field, which is uniform. Okay. So I should make that very clear. H. So here, let me say that very clearly. Because that's another thing. We are very lax about H and B, and it doesn't usually matter. But now that one of them is 0, we should be very clear. H is, let's say, uniform. And this is the external field. And this is generated due to, let's say, 2 large magnets. So there is N and S, and so it's just some constant field. And B is the total field. So B is now equal to H plus 4 pi N. So when I drew that with the superconductor, those are actually lines of B, which is a function of R. So in this picture here, these are B of R. And if I had to draw N, N would be basically finite in the superconductor, canceling that H exactly. And the supercurrents were this much. Okay. Now let's see if we can write down some equations to describe this. Okay, so what we have is basically our Ginzburg-Landau equation 1 turns out to be, actually, before that, let me just write down the free energy. So what you're doing all the time, it's like saying, now I have an electron in a magnetic field. What is the Hamiltonian? That's the same question we are asking. So what is the free energy now of something which is in a magnetic field? And so this is going to look something like this, F0, some constant, plus, you see, because I have R dependence here, I'm putting a constant magnetic field, but it generates a response necessarily that varies with R. I have to now write down a more generalized free energy, which is an integral over all R. I won't dwell on this too much except to just write it down so you see where all the terms are sitting. Okay, so this is like your P minus EA, except these charges are effective charges and so on. So don't worry about that, but it's this minimal coupling, just the way an electron would have coupled in this manner. Now it's the condensate which is coupling in this manner. Is this familiar? This P minus EA coupling?
What is E star though?
Okay, E star is just 2 times microscopically because it's the Cooper pair charge. So wherever you see E star or N star, these are essentially the Cooper pair mass and charge. Oh, sorry, 2 times 10. Okay, so that's the equation. And plus, no, I have to add one more term. So this is just telling you how the order parameter couples to the electromagnetic field. And then there is a cost in energy, which is, if you remember, when you have magnetic fields, there's a B square cost in energy. Magnetic fields also carry energy. And so we have to add that. So plus some, let's say, since I'm writing everything in terms of A, let me just write 1 over 8 pi del cross A square. And all of this within that this bracket here. Okay, so B, my magnetic field, is nothing but del cross A. So this is just B square, which depends on R over 8 pi.
You mentioned Zeeman earlier. This is like,
Yeah.
this should be like M dot B. Why is it just B squared? Just
Oh, this is not that term at all. This is just the electromagnetic field lines carry energy, which is E square over 8 pi if there was an electric field, and a B square over 8 pi if there's a magnetic field. Okay, so that becomes our free energy function now. And now we have to work, it's the same kind of thing we have to do now. So I'm just going to give you the idea for how this is our complete story now. This is the equation you would write down for us. This is the full Ginzburg-Landau equation. By that I mean, it has everything. It allows for order parameter to be varying in space. It allows for the order parameter to interact with the magnetic field. It has everything. Now you can take variations, and basically you can get 2 equations. Ginzburg-Landau 1, which comes by doing variations in F with respect to psi star. This gives equal to 0. This gives one equation. And the other one is Ginzburg-Landau 2, which comes from delta F by delta A. And that is equal to minus 1 over C times the current. So this is the new equation. Okay, that And this also should be, I don't know if it is familiar or not, but if you had an equation like this for an electron, let's see, if you had a non-interacting electron, it would look like this. And if I take derivatives with respect to A, I would get del psi, psi star del psi minus psi del psi star. That's the current operator that you would get. And that's exactly this equation. Okay? So these are the two equations that govern now the behavior of the superconductor in a magnetic field, as well as near walls or anything. It's the complete story. What we are interested in is not really solving it in every possible way. I'm going to now look at where is the Meissner effect sitting in that, and there is another length scale that we will see emerging from this, which will be the length scale. We said that, so there are two things. What we are going to do next time is look at the Meissner effect. And that's sitting here. It's a very simple equation which is sitting right here, which I can get if I just make the assumption that it is a bulk superconductor. So there are no gradient terms if I take a bulk superconductor in an external field. And then what you can show is that the equation you get is J is equal to some set of terms times the vector potential. Okay, so I'm giving you a little preview of what we will do more carefully next time. But this equation is sitting here. If I take this derivative with respect to A, I get the current, and what you find is that the current is minus something, some set of constants times A. And this is very important. This is what I was saying earlier. When something has resistance, J is proportional to E. And you know that E and A are related by a time derivative. So dA dt is the electric field. So there is an additional, so dA dt, I don't remember some constants, but dA dt is basically the electric field. So this gives you an I omega times A as the electric field. And this I omega basically tells you that what you have is acceleration. So I will go through that next time. But this equation is, I will get you those constants and so on, but this is called the London equation. Okay, now London just wrote it down by fiat, because he said, we don't want resistance, so J must be proportional to A. This was his intuition. But in a way, there's a systematic way to derive it. It just follows from this equation, which is basically describes the order parameter in a magnetic field. You take this variation, you get an equation like this for a bulk superconductor. This minus sign is the origin of that diamagnetism. Okay, this is a very nice, very beautiful equation, and sitting in this equation is another length scale that we will talk about next time. And that length scale is a measure of the following. We said that this superconductor will generate currents. These currents are not everywhere in the superconductor. They are on the surface. So essentially, there is a sheath. This is my superconductor. There is sort of, if I look at the current, it's kind of on the surface. So it's on the surface and it decays as you go in. So as you go in, the currents decay on some scale. So the way to think about it is a surface current which is moving, and the surface currents decay as you go inside on a certain length scale which is not the correlation length. This is what is called penetration depth. It's what it is. It is a penetration depth. The depth over which the magnetic field is penetrating. So it's not correct to say that in a superconductor there is no magnetic field inside. There is a magnetic field over a length scale, which is this much. Lambda. Lambda L for London. So there is a magnetic field which penetrates over a certain length scale, and that's the length scale that the currents are desperately trying to cancel the magnetic field, and then beyond that, there is no magnetic field in the superconductor. So there's a thin sheath that still has the currents. So next time we will derive that and get something more quantitative, and then I'll make connection with experiments and tell you how we get these different